Hi there, guys. This is Unit 11. I'm going to attempt to do 11A, B, and C here, although I might split it up. This is essentially integration. Integration is the other part of calculus. Differentiation is the first part. Integration is essentially the inverse function of differentiation. Some of you might know already that integration relates to areas underneath curves, and that's what we're going to build up to show today and then to use on our calculators. Okay, so this is called approximating irregular spaces, integration, and differential equations. We definitely won't be getting to differential equations today. Okay, so I've just taken this from the exercise before 11A, and you can see here that we're trying to work out the area underneath a curve, so this area here, and on the left-hand side, you can see that we have these green bars. If we added these green bars together, we'd have an underestimate in this case. And to the right-hand side, we have an overestimate. And that's because they're taking the start height of each of the bars in the first case, and they're taking the end height of each of the bars in the second case. Now, in both cases, we could come up with a formula here and say that your area is approximately equal to, so the area underneath the curve, is approximately equal to the sum of I is equal to 1, in this case to 6, but let's say n, of your heights, so yi, times by your delta x's. Your delta x would be your small change in x here, in other words, the width of the bar. So, for example, this would be the height of the first bar, y1. This would be the height of the second bar, y2. This would be the height of the third bar. This would be the height of the sixth bar. Okay, so let's take that back for a second. So the heights are represented by, let's take it forward. Okay, so the heights would be represented by yi, so that would essentially be you putting in your x value into your y function, or your f of x if you like, to get out your heights in each of the cases. Right, and then we could approximate the area using these bars by summing together the area of these rectangles. Now, obviously, this is going to be your lower bound here for the area, and this is going to be an upper bound. But if we had more bars, then we'd get closer to the real area in both cases, because we wouldn't have such big spaces here if we put in another bar. Okay, so if we doubled our bars, we'd get closer. And so this overestimate, this underestimate and this overestimate will get closer and closer to the real thing if you brought dx to be smaller and smaller. So in a sense, it doesn't matter if we use yi to be the first height or the last height in the bar. That's not going to matter, because if we make our bars smaller and smaller and smaller, thinner and thinner. Okay, so what we're going to do is say, so on the first one we would approach the answer from below, and the second one we would approach the answer from above, but we would approach the answer. So now if we could actually take a limit, okay, as our delta x, or height as we were using before, delta x tends to 0 of this thing here, then we're going to actually get, in our case it's 1 to 6, but the general formula is summing from 1 to n of yi delta x. If we can take this limit of this thing, then it won't be an approximately equals, it will be an exactly equals. If we can take this thing, tend this thing to 0, we have infinitely many strips, all infinitely thin. Now, this is basically our integration, but integration we write down like this. We say, instead of the sigma sign, we sort of stretch out the s, the sigma, s for sigma, and we say this is all of our yi's, this is our y now, and the dx, the delta x becomes dx, like in differentiation. And we don't need our yi's anymore, because we're going to take infinitely many of these strips, and we say that this will go from the start to the end of our category of our x value. So this would be A and this would be B here. So this notation here is talking about summing together infinitely many strips or rectangles, but this is the notation which we use in integration. And it's essentially saying the same thing, a little bit like when we go from dy delta y over delta x, and we're taking the limit when delta x is tending to 0 of this thing becomes dy dx. That's now a thing. This is the same here as well, but this is our integration representation of this thing. Okay, well, there's a lot of theory there, but let's have a look at some of the questions in the book. And first of all, let's just check that I've talked that one through all right. So they basically give you an example. You can look through this in the book, and you can see that they're taking two versions of this. They get you to do a little exercise, and then they say, well, let's use more bars. And then they say, let's use even more bars. And what do you notice? And of course, we're getting closer and closer to the real thing. Okay, here we go again. This is just to say that I wasn't making this thing up. We've got the area is equal to these rectangles summed together. And if you take the limit as dx tends to infinity, it tends to 0, then your area becomes exact and approximately equals 2. And then they say, well, if we change this limit to an elongated s, they say the delta x becomes dx. And essentially, they don't give you a proof for this, but they say that this is the same as this. There is no formal proof here. They're saying, let's write it like this. Okay, so we've kind of skipped a formal proof, but we're doing that to get straight onto the questions. Okay, well, let's have a look at one of the examples here. And they build you up pretty slowly through these examples, which is why we're doing a lot of exercises all at once. They're all fairly straightforward, in fact. So example 1 says, write down the definite integral that gives the area of the shaded region. So this region here, let's snatch this one, capture this. Example 1. Oh, computer's going a bit slow today. Okay, so write down the definite integral that gives the area of the shaded region. So what they're asking for there is basically saying, well, you could say, well, we're doing the sum of all of these infinite yi's times by your times by your delta x's, and we could limit take the limit as delta x tends to 0 of this thing. But frankly, that's not what they're asking. They just want us to write it in terms of the integration terminology. So this is just integrate this from starting at 1. So you could say x is equal to 1 here, x is equal to 4, and then we're using our f of x or our y dot, so with respect to x. That's what they want us to write. Now f of x in this case is the same as y, and we can write in there x plus 6. And then some people, like on your calculator, you'll need to put in brackets, but people understand that if you put dot dx on the end, it doesn't just mean 6 times by dx. That's not a dot as in times. That's just to say, I'm doing this thing with respect to x. So you always put on the variable that you're doing this with respect to at the end as well. So that's what it means. Okay, now you can see that that's the same as this, except for they haven't said x is equal to 1 and x is equal to 4. They've just written 1 and 4, and that's completely fine. You don't have to write x is 1 and x is 4 at the top. Okay, so in the second one, it says calculate the definite integral by using the formula for a trapezoid. They mean a trapezium, it's just another word for the same thing. So they are not doing any integration here. They are not doing any inverse differentiation. We will come to that later. All they're doing is saying, oh, by the way, this is the same as the area of a trapezium. Well, what's the area of this trapezium? It's the height of the trapezium, we turn it the other way up, which is 3, times by the average of the 2 parallel lengths. Well, that's a length of 2 and a length of 5. So 2 plus 5 times by your height divided by 2. That's just this formula here, okay? That's a half A plus B times by H. It's the area of a trapezium. Nothing tricky in the first case. Those two things should be the same. Okay, in this first example. Right, so let's look at the questions here. Now, in terms of the questions, it is a good idea to do one of these questions. I probably wouldn't do the second of these, but they just get you to do one of these practical examples, building this whole thing up. And I still think this is pretty good. So question one is quite a good question. They said find the equation of this sector in the form of y is equal to fx. Ooh, find the equation of this sector in the form of, okay. Oh, all they want you to do there is a rearrangement of this formula here. Okay, so it's not the area of a sector formula which we're using just here. So they just want a rearrangement of this. So you've got y is equal to something, and you've got to decide whether you're going to need to do plus or minus. You take a square root. Write an expression for the area in this form here. So we're going to go from 0 to 3, and we'll put up for x in here as well, which will be your rearrangement of this, y equals something. Okay, and then they start saying, come up with the values for y for these particular values of x, from 0 to 3. And then they say, use the table and the following diagrams to calculate the sum and the areas of the rectangle. Form a lower bound and an upper bound. They mean use these things here. Come up with a lower bound from this one, come up with an upper bound from this one here, and use the values in your table to get the sum of those rectangles. Then they say take that, you can follow this question through, right? It's just building you up at the moment. This is not integration just yet. They're trying to get you to write things like that. Okay, next little bit, they're talking about using the GDC. Okay, so for this question, using the formula for the area of a trapezium, again, find this area. Well, that's not going to be tricky. Smaller. Capture it. That's playing up again. Really going slow today. Okay, so use the formula for the area of a trapezium. Again, that's going to be dead simple. You need your two parallel lengths, that's this one, and you'll get them from substituting in these two values into the formula. And you'll have a height of this trapezium, which is just the difference between the 3 and the -1, so a height of 4 there. And then you can use the area of a trapezium. That's dead easy. Okay, use the integral function on your calculator. So for the first time, you'll be doing this thing here. So on the calculator, there's two ways of doing this. And, come on. Here we go. So on the calculator, there's a couple of ways of doing this. Sorry about everything being slow today. I've already restarted the computer. I think I'm going to need to stop and restart again though. Okay, that's not what I wanted to see. Here we go. So on the calculator, basically there's a couple of ways. You can get your calculator while you do this. There's a couple of ways of doing this. You can do it through the menu, and you can take it through calculus, and you can take it through setting up integration there. Or there's an alternative way of doing this, and that's that you can use the key, if you can just see what I'm hitting here, next to the 9. If you click on that, it will come up with all of these different options of things which you can set up. And if you look across to, here we go, I've just clicked on it there, sort of middle-ish there, there we go. Oh no, that's the summation, where we got the integration sign. Integration is there, bottom left, okay? So we've got a summation sign there, we've also got a integration sign there as well. So lots of little templates which you can use to write these ones down. But it should be pretty straightforward that when you type this thing in, yeah, you just type it in straight away. You can either go through the options and go to calculus to set it up, or you can set it up using those keys. It does not matter which one you do. You do not need to put a dot in between the function and dx, but they always give you brackets to put in as well. But you do need to put in where you start and where you end on this one, and then of course you can just evaluate by pressing equals. Sometimes if you put things in, like if you needed to put in this function, it won't work it out unless you put a times in there as well. So just be careful about when you're adding these things, when you're putting these ones. I suggest you have a go at this. Okay, next little thing, see how far I can get without the computer completely crashing. Right, example 3, let's just keep it on here. So consider the area of the region enclosed by, here we go, this one here, okay, where there's going to be a times, by the area enclosed by the curve and the x-axis. Well, first of all, we need to know where the curve is in comparison to the x-axis, relative to the x-axis. So on your GDC, you're going to need to find where that region is, come up with a little sketch of that as well. And you can see, well, you probably know that this crosses at 0, 3, because that's your roots from this. So 0 and 3 are going to be your limits in this case. Write down the definite integral that represents the area. There's my function that goes inside. There's the dx at the end. There's 0 and 3. Pretty straightforward. Let's find a, or you can type that into your calculator and press equals. Okay, example 4. I'm going to stick on here and talk through it. Example 4, the region bounded by the curve here, the x-axis and the vertical lines, x is equal to -1 and x is equal to a. Right. Okay, this becomes slightly more interesting because it's now asking us to solve a problem with integration. And yet we don't know how to undo integration yet. But you can do this one on your calculator. So although you can't undo this by, well, maybe you know differentiating both sides, but I'm not going to go into this just at the moment. But yeah, you can type this one into your calculator. Now, how do you type that one in? Because you're going to need to solve to find out what A is. Because it tells you that the area underneath this curve is 12. You need to solve for A. Now, when you type this one into your calculator, you can put in, this is the way I did it. Let's go back to the picture. I think I'm not having much joy here. Now, which one was it? Here we go, got it up on here. This is terrible today. Sorry, hopefully you just flick it forwards. Okay. Having a mare. Right, okay, so this one here. So I've done guys, this is really getting frustrating. So doing an n solve in this case, and instead of using a, you can use x. So we're saying from -1 to some x value further down the curve, and we're doing this with this respect to x, and here's our function inside. So you can set up your n solve like this to solve it. So you don't need to put in a, you can solve this in terms of x. This is essentially an equation in terms of x. You can see I messed up in the first place because I didn't do x squared. Right, okay. Okay, so that's that one sorted out. That's pretty straightforward. Right, 11B, you can have a go at some of these questions, and we'll do 2 lessons on this in class. I'm going to, for my sins, I'm going to try and do 11C here as well. We talk about negative integrals. This is one small extra step. And there's essentially another formula for this, and it's this one here. So let's just take this, see if I can take this, click forwards. Okay. Okay, and you basically have some absolute signs here, or modulus signs, these symbols which you've got here. So basically, you should know that you can also get negative areas. So if you're trying to integrate between here and here, and you're just above the curve, when you integrate that, it will give you a positive answer. If, can't even undo here now. Okay, if you have this below the curve, then you do between A and B, then it will give you still just the same as this thing here between A and B. Then this one will give you a negative answer. Okay, so if you do instead, if you use this, and we say, well, let's take the modulus of this function. Well, the modulus of this function will essentially take it to the other side over here. We'll take all those negative values and make them positive. So it will put them up there. Ultimately, will give you a positive area. Now that also works if you are going through the axis. So say, for example, we were interested in working out this area here. We'll get a negative area plus this area here. But say if we wanted the area which is trapped between the curve and the x-axis between A and B, then if we did just normal integration like this, we put our function in, then it would add this negative area to this positive area, and you'd end up with a slight negative area in this case here. Whereas if you do this, so if you put modulus signs in, so that can be found through the same key, which is next to 9, by the way, to find your modulus brackets, then it will make this whole function positive. So it will make the function up here positive, essentially, and move this to this side. So this entire thing here to here will be your new function. So when you're integrating between A and B, it will give you your total area underneath the curve there, all made positive. So if that's what they want, the interval which is bounded by the curve and the x-axis, then it is always best to use this function here. And it's always a good idea to check on the calculator what this function is looking like as well. And see if it's got any roots, and see if it's below the axis or see if it's above the axis too. Guys, I'm going to see if I can go one more question in. Okay. So let's have a look at this. Before they get to 11C, they give you one example. And they say, sketch the curve, in this case, from 0 to 3. Find the area. So, I mean, that's easy. That's just on your GDC. You can come up with that. Find the area of the region bounded by the curve. Well, there you go. It's just put your f of x inside these modulus brackets or absolute, find the absolute value of that, absolute brackets. These modulus brackets, these straight lines here, which you're using, we're still doing it between 0 and 2, and that will give us this answer here. I think they put an approximately equals to simply because they've given it to 3 significant figures. Okay, guys, sorry about the glitching of my computer. But that's that for the moment. You need as much practice as possible on A, B, and C, and we'll help you with that over